I have the honor to be the first speaker today, which is exciting because you saw yesterday a lot of chemistry and you saw engineering, but ALD, the work with ALD is actually everything. It's physics, chemistry, engineering, sometimes biology. So I guess most of you are chemists, right? How many are chemists here? Wow. Physicists? 50-50. Social scientists? Linguists? No? Okay. So we have to deal with both of them. And the good thing is, here there are a lot of physicists and lots of chemists, so you can have in this project the benefit to talk to each other and to learn from each other. You need to know a bit about everything. You cannot just rely on chemistry. That's one important point, but you need also to deal with physics. I'm a chemist, so forgive me if I don't derive every comma here in this next couple of slides. So I take things for granted just because it's there. You know, physics for me is nature. Something falls down. I don't care why an apple falls down. It falls. So I will show things which we consider here important from the physical point of view. If you want to go into depth of that, you will find the references there to derive all of those equations. An important point in ALD is to not only do depositions, but to deal with diffusion. And diffusion can have many, many different aspects. And when you do ALD processing, this is a slide which I showed some time ago at an ALD conference. You expect to have really a pinhole-free and conformal coating by ALD. This is what everybody claims being the main issue, the main point in ALD. But in many circumstances, you will not really meet your expectations. So you will have coatings which are not perfect. And of course, this can have several reasons. And one, of course, is the normal reason that something went wrong, so your process doesn't work properly, because of your precursor delivery system, because of your chamber temperature, because of non-homogeneity, and so on. So you can check this very easily from the engineering aspect. But you have also to deal with the physics and the chemistry and the combination of those two if everything else from the engineering aspect works well. And many of those things are really related to diffusion issues which you may encounter during your processes. So now, what kind of diffusion processes can happen during or after the ALD process? I mean, you are preparing samples, you are coating your substrates, and you don't, in many cases, want to use them just as they are. So you are doing samples, you are making samples for a certain purpose. So you don't only have to account for diffusion phenomena during the ALD process, but also in certain post-treatment conditions. It doesn't help you if you have a perfect coating before your post-treatment. If you need to treat your sample in order to have a functionality, and during this post-treatment you again have something else which destroys the sample or makes it different than it should be. I put together those diffusion phenomena which I found being of interest and of importance for most of these, let's say, special processes where you want to prepare some functional samples. And those relate mainly to surface diffusion. This is, I think, a very common thing. Go a little bit into that. This is happening during the process. Then you have the possibility to diffuse material into a substrate. This is also happening during the process, in most of the cases. Diffusion into pores is a very critical issue if you don't have flat substrates. Again, this is an issue which happens during the deposition. But if you want to treat your sample after the coating, then you may have another set of diffusion processes. For example, diffusion of material at interfaces between two materials. So your coating and the substrate, for example, or a multi-layer coating. And you may have also something happening through the coating, either this way or this way. So these are the post-process diffusion phenomena which you need to take into account and to just think of in case that you want to have a functional material. Okay, let's go first of all into those diffusion phenomena which happen during ALD processes. So case one will be the surface diffusion. The chemistry which you learned about yesterday is a very important point to grow coatings. However, the most critical point in order to grow a film on top of an ALD or of a substrate is to have functional groups where the precursor can attach. This is something which I think is self-explaining and it's easy to understand. However, what happens if you have a substrate which in some way is inert? Inert in the sense that there is no chemical functionality, so your precursor cannot bind. Normally you would say it will bounce away. The precursor will come from the gas phase to the substrate. There is no functional group, so it will dissolve again. Of course, that's the ideal case. In an ideal case, if you completely inertize a substrate, you will not have a coating. But how many cases are ideal? So that's the next question. In normal cases, you will not only have a completely inert surface, you will have defects. And what happens there is, you have a precursor coming to the surface, it may physisorb, it will diffuse. In the ideal case, it will redesorb again. So this is the ideal situation. But in the non-ideal situation, it will diffuse further. It will come to a certain point where you have a functional site, the defect site, and it will nucleate. And from then on, you have your nucleation spot being the substrate for your ALD. That means you don't care about this surface anymore. Your ALD growth will happen here. And it will happen here by being fed either from the gas phase with the precursors or through the substrate. That means you need to really also consider this possibility that the precursor will attach to the substrate and will diffuse to the next point, nucleation point, bind to your spot and start growing the new cell. This is something which is not new, and I think it's very easy to understand, especially from the physical point of view. Many of you have learned about STM, AFM, and so on. Many people do STM investigations on surfaces with atoms deposited there of one material on top of another, investigating Kondo effects and whatever, impurities. And they do this at low temperatures, at really low temperatures. And the reason for those low temperatures is, if you deposit an atom on top of the surface, if it's only physisorb, so not chemically bound, it will diffuse on the surface in case that you exceed the activation energy for diffusion. So here you need, for the STM guys, they need to stay at a very low temperature in order to fix the freezing molecule. In ALD, this is typically not the case. You operate at temperatures which are, well, from room temperature to 100, 200 degrees. That means you are in a regime where those molecules which attach to the surface are starting to diffuse and to move around, and then they either dissolve or not, or they bind. And this either dissolve or not is dependent on this graph here, just as a rough scale, or rough idea to give you an idea of what it looks like. So if you are operating in a temperature regime, which is here, giving this thermal energy, above the activation limit of hopping events from point A to point B, but below the energy which you need for desorption of the atom or the molecule, then you will have this diffusion, and this diffusion will lead to a condensation or binding of the molecules to defect sites, and then starting to grow and nucleate and grow islands or whatever on defect sites. This diffusion is temperature dependent, and well, here the Arrhenius equation is the base principle for having the idea on what is the temperature dependence on those hopping events. I think this is not really so much important. This is just for you to have in mind. And important is to know that it's, so you have a binding, a physical binding of molecules there. Typically they will dissolve, but in some cases, if you have defect sites, they will also grow. Again, sketching here, what this means. Your precursor molecules will come to a surface. The surface is not ideal. It may have steps, it may have kinks, it may have physical or chemical functional sites. Upon inserting enough temperature or thermal energy, those physisorb molecules will start to move around. They will go to those edges, the steps, chemical or physical defects, and start growing around there. And what kind of defects you may have is just outlined here, so you have kinks and steps or chemical functionalities. Now, the point is that this is happening, for example, if you have carbon nanotubes if you have graphene, if you have such materials which don't have oxidized functional sites, so you have just a bare carbon surface without any functional group or any kind of dangling bonds, edge silicon, and so on. And normally on such surfaces you would not like to have a parasitic growth somewhere. But sometimes you want to have it. So you can have those growth spots desired or undesired. And if you want to have them desired, you need to intentionally introduce them. Oh, I swapped this one. So if you want to introduce them, we have several possibilities. So for example, on a silicon wafer, if you have an edge silicon wafer, you can introduce such functional sites in terms of OH groups by treatment with Piranga solutions, for example, localized treatment. You can oxidize on certain points, so you will have those spots. So you can use this substrate to use your molecules and to bind them to those local sites which you oxidize, and then start growing materials on those spots. It's a sort of approach for also area selective ALD. Also, an initial approach was to treat silicon wafers with microcontact printing, so you can have, for example, self-assembled monolayers printed on top in line shape and arrow shapes. And those parts will be either functional or non-functional, depends on your molecules. And on those places you won't grow, so the precursors will stay away from there, but they will grow, they will diffuse, and they will grow on those spots where you have functional sites. A bit complicated to understand, but if you have questions, we can talk about it later. Another point is, for example, carbon nanotubes. This is some of our work. If you have carbon nanotubes, you normally, if they are clean, if there are no surfactants, if there are no defects, you will not be able to grow material on top. In order to grow material, you can, for example, use ozone. This ozone will introduce defect sites, and those defect sites will generate oxygenized carbon there. And this is the binding spot. This is what you see here. This is the carbon nanotubes, pristine. And after this treatment, you can grow material. These are the small spots here, which grow just on those defect sites. If you continue growing, you will have a film. The fantastic thing here is that you can even grow small particles. And those particles, again, because it's ALD, they grow layer by layer. It means the sizes of those particles which you grow on those spots are really precise in size. This is very well defined. Another approach is here also to use biomolecules for functionalization. That means here the guys from, this is I think the group of Stacy Bent in the US, they did it some time ago. They wrapped carbon nanotubes with DNA. So carbon nanotubes again are not functional, they are inert. You cannot easily do ALD there. But if you wrap DNA around, and DNA is a biomolecule which has functional sites, you can deposit on DNA. That means you can use this as a substrate for coating DNA, for coating carbon nanotubes. And in this way, ALD functionalizes for nanotubes. It's fascinating. It's a bit tricky, but here you can do, let's say, the little bit more non-regular ALD. In ALD, you really want usually to coat the whole surface. Here you have the possibility to functionalize sites of the surface and to do area selective ALD, not in terms of industrial area selective, as Paul showed yesterday, but I mean spot defined area selective ALD. So this is, you will not be able to define here exactly where the spot is, where a particle grows, but you will have a high surface area, for example, for catalysts. The catalyst balances, so this is a real thing. And you can also, this is the slide which I skipped just before, you can use natural substrates. And this is, I like this work very much, was one of my students doing some years ago. It's an eye of a fly. It's a Drosophila fly. And the eyes of the flies, the tacet eyes, they have a hydrophobic part here and a hydrophilic part in between. So these are functional sites of the eye, which just biologically given. And if you try to do ALD, and this is zinc oxide, you have no deposition or almost no deposition here, but it all deposits just on those sites here. It means you have also here the precursor attaching to the surface, diffusing, and then binding to those functional sites here and starting to grow. This beautiful hexagonal structure here, which is, I don't know what is a good product, it just looks nice. So, we never published it stuff. Okay, so, yeah, you need to know that, and I think from this part, the surface of the substrate is a very important point. not only the physics, but the chemistry, here in this case. The chemistry plays an immense important role. You have functionalities there, or you don't have them. If you don't have them, you can have a diffusion process happening to the defect side. So you may wonder, you produce a sample, you may wonder, why the hell do I have a deposition on this spot? There should be no. Keep in mind that the substrates are never perfect, or almost never. And if you have defects, you will have diffusion phenomena, and at some point, the precursors will come to your defect, and it will start growing there. And then you will have some features. And those features may be undesired, maybe you end up with something nice like that. So this is really cool. So that was surface diffusion. I hope this was not too far away from your interest. Let's go further. Case 2. Diffusion into pores. Again, it's about the substrate, but I'm not talking now about the substrate chemistry, I'm talking about the morphology of the substrate. ALD is known to make really nice conformal coatings. That's what everybody claims. So you can go into high aspect ratio structures, you can do perfectly conformal coating into high aspect ratio structures. You can do it. Yes, that's true. And here again some examples from our labs. This is a sponge, it's a sea sponge coated with titanium oxide. And you see here, this is a cross section. Inside here, all of those white lines, this is all titanium oxide, which was deposited through the sponge into the depth of the structure. That means these are extreme aspect ratios, and you can really get into there. And doing a very nice coating. Another example is etched silicon wafers. So undulated etching, so it was photoelectrochemically etched and made those nice balls. Then you can do a coating, a nice coating with ALD, and then you etch away the substrate, the silicon here in this case, and you end up with those very, very nice chains. So it works. This can really work. The problem is that you need to really think about how to set up your process. Because before this work, we did this work. It's porous aluminum oxide, AAO, and we did a titanium dioxide deposition. And if you take a look from this bird's eye view, so this is on top of the AAO, you see the pores very nicely covered, coated with titanium oxide. You have those very nice tubes. But if you make a cross section and etch away the aluminum oxide selectively, just to remain with the titanium oxide, then you see that out of a 100, no, it was probably, no, it was 50 micrometer deep structure, only about 1.5 micrometer depth was coated with titanium oxide. So you need to know how to set up your process parameters in order to get deeper than that, because it's not just self-understanding that an ALD process will coat everything, whatever you have inside there. That means you need to care about the aspect ratio and how to make the process having a really good step coverage in high aspect ratio structures. Coming to the aspect ratios and the step coverage, this is just a sketch to make you understand what I mean with step coverage. It is basically the ratio of the coating on top of a structure divided by to the coating in the depth of a pore, for example. If this thickness here is the same as here, then the step coverage is 100%. That's what we want to have. If this deviates, then there is something wrong with the process. Now, how can you get ALD having a step coverage of 100%? Well, you need to think about several issues. One of them is, for example, the chemistry. That's the utmost important issue first to think about before you set up a process. What is your chemistry doing, and can your chemistry have an impact on your step coverage? And this is very much dependent on the stability of the precursors. You heard a lot about stability by Nico Rittala yesterday. Many precursors which are stable at certain temperatures. Some of them are not. Some of them are stable over short time. Some of them are stable over a long time. The essence of all of that is that the stability of the precursor needs to be considered. And if you, for example, operate with plasmas or radicals or ions, which are very short-living species, then you can also understand from the physical perspective that if you have very high aspect ratio structures, those will recombine before they reach the bottom of a deep pore. If you have a very, very high aspect ratio and you have extremely radical, energetically active species, they will be combined. They will not reach the pore. So therefore, it is always tricky, and I think Erwin Kessels is not here to complain about it, but it's not something negative. But what I mean is, if you operate with plasmas, it is way more tricky to have high aspect ratios conformally coated than if you work with thermal ALD. But even in thermal ALD, you will have problems if you really go to aspect ratios beyond 1 to 10,000 or whatever. Chemistry is an important point which needs to be considered. Think about your chemistry which you are using. Think about the radicals and plasmas which you use. And many of them, if they are really short-living, you will not be able to get into deep pores. So the conformality in high aspect ratio structures will be very poor in that case. But if your chemistry is okay, then you need to think further. And further means you need to think about how long time do you need to give your precursors to diffuse. And now we are back again to the diffusion phenomenon, to diffuse into pores. So imagine you have a big pore and you have some gas molecules and they are just diffusing there around. They need to enter the pore and then they need to get into the depth of the pore. And this requires time. This requires time for the process scale. Many people think, okay, I have my pore, so the deeper the pore, the longer it needs to expose, so the longer I need to give the time for the precursor, and this is correct. But what is the extension of the time you need to give the precursor? You typically tend to think it's linear, but it's not. There were 3 models set up for that purpose. So one was by Gordon and by Kim, and also a Monte Carlo simulation by Jeff Elam. I think there are some more models around, but these are basically enough to give you an idea on what the essential claim out of those is, what in terms of time you need for the process. So if we go to the Gordon's model, it is a purely, let's say, simplified physical model. You think about the gases, you think about Knudsen diffusion. So you have the diffusion of the molecules and you have no collisions, so you just ignore collisions between the molecules. You think about the pore. You have the mean free path of the precursor molecule is much larger than the pore diameter. These are just simplifying preconditions. The sticking probability for the reactants on the surface is 1, which means if a molecule comes to a surface, it will bind instantly and irreversibly. That's the claim of here, so it means you also simplify the chemistry. Of course, all of this is simplification. That means you will never get a real value, really valid value in terms of number. But it will give you an idea of how much time you really need on the order time. So the sticking probability is 1. The dose of the precursors is enough to reach the stoichiometric amount. This is what you always need to have in terms of ALD processes. You want to have a minimum of molecules to have a full separation of the surface. Otherwise, you have an undersaturated process. So that's all usually valid for all ALD processes. Now here, for this, if you don't have experience with ALD and the dosing, you really need to think a little bit about the surface that you have. People sometimes tend to underestimate the surface area which they have in their chambers upon coating. Imagine you have such a porous aluminum oxide, which I showed before. This kind of thing here. A small chip, depending on the pore size, of course, that you etch here. A small chip of, let's say, 1 centimeter diameter and 50 micrometers depth can easily have several tens of square meters surface area, depending on the pore diameter. So don't underestimate the surface that you have here for coating. And in agreement with that, you need also to select appropriate dosing times. That means appropriate amounts for dosing the precursors. That's really, really essential, because if you don't have enough precursor, you will never reach surface coverage, proper surface coverage. And for this here, also the reactants at the pore entrance are available in sufficient amounts and so on. So this is, I think, all what you need in order to make a model as easy as possible and understandable. Now, if you start from those assumptions, according to Gordon's model, you will end up with such a formula. And this formula tells you that the time for exposure, given with the pressure of the molecule, the partial pressure that you use, contains two factors. One of them is related to the flat surface, but you have the other one, which is related to the pore. And if you have a pore with a higher aspect ratio, this term here prevails. That means the time which you need to expose your substrate to the precursors scales with the square of the aspect ratio. And this is very important to know because people sometimes really tend to think it's a linear relation. It's not. It's a square relation. That means you will have an enormous extension of time just by increasing a little bit of the pore length. And you need to keep this in mind, otherwise you will never have a really good coverage there. So the diffusion here is really limited by the aspect ratio. All of that, the derivation of the whole story here, you can find in this paper. It's a very nice paper from 2003. It's quite old, but it's very nicely explained how to get to this formula at the end. Okay, so we have a square relation here according to Gordon's model. How about the others? Kim's model, it's another approach, it's a different approach. Doesn't start from a pore as such and looks into the entrance of the pore and the molecules diffusing into the pore, but it goes the other way around. In Kim's model, you take the pore itself as a coordinate system. And you take any point in the pore as a starting point from where you can calculate what do you have there. That means what happens over time if you have a certain dose of precursor, how many of them will touch this point in the pore, and how many of them will stick to this area. Now, it's a little bit a different view, so you have also to consider the flux at a given point, you have to consider the sticking probability, so the ratio of the hemisorb species to those which do not hemisorb. He also considered, which was very nice, various mechanisms for re-emission. That means not all of the molecules will really bind directly, some of them will reflect and some of them will bind. So all of this is put together in this paper here, in this derivation of this formula. And at the end, you will end up with something like that. So the time here, the time for the exposure here is in the exponent of the dosing time. And this is maybe not directly comparable, also the approach is not directly comparable, but what it tells us here, similar to the before, it's not a linear relation. There is not a linear relation between exposure time, diffusion time, and the set coverage. If we go to the third model, it's a Monte Carlo simulation, so it's not really just a real physical derivation in paper. It's a Monte Carlo simulation, but also regarding the Knudsen diffusion here, so simplified factors are the same as in Gordon's model. The ALD precursor is the limiting reagent. The sticking coefficient is included, so it's a little bit of an improved model. Also, something which is very important, as I said before, the aspect ratio of the pore defines your exposure time which you need. But during coating, you are shrinking the pore. It means you are enlarging the aspect ratio. So you will, in principle, if you want to make a perfect process and you are giving the exact amount of precursors which you need, you will have to have a dynamic process. That means a dynamic process which with every cycle or every 3 cycles is going to extend the exposure time because you will need more, just because the aspect ratio shrinks. So this is also considered in this model, and particles are allowed to hop in and out, so this is also a more, let's say, practical case here, which is considered, so not only in diffusion but also out diffusion. But at the end, all of this is probably going too detailed before, but just to give you an idea on that, the Monte Carlo simulations also scaled with the square of the aspect ratio. So whatever you do, whatever you try to simulate, you will end up with something which is square or even more. The diffusion is a very, very important issue here for the precursors if you go into corrugated structure. The higher the aspect ratio, the more exposure you need. And the aspect ratio of your pores or your structures is really a very, very important factor here, because you need to adapt your process and you need to give the precursors enough time to diffuse from the gas phase into your pores and into your structures. So, if you want to go practical, you have proper parameters you want to measure whether they are okay. Then how do you do that? So, just a few examples on how to measure the thicknesses of coatings. Of course, you can do cross sections and you do SEM images. You take a top and the bottom of a pore. In this case, it's just an example from literature. There is copper sulfide deposited on top and bottom, and they were just comparing the thicknesses here. And the thicknesses are just with a small error. It means the coating, the process setup was really good. Of course, the pores here are rather big. In ALD, you sometimes really go to much smaller structures, so it becomes more difficult then to really look into that. But okay, SEM is a really good tool to take a look into the thicknesses. What you can also do if SEM is not easily possible in a cross-section mode, so this is well, this is also SEM in a cross-section, okay, but with EDX coupled. This is work from Jeff Elam, and what he did here is to coat pores of porous alumina, as I showed before with titanium oxide. But he used various exposure times for an initial coating with aluminum oxide. So imagine this is the pore here. These are the pores. Now, if you expose to TMA to grow aluminum oxide first, so first you have TMA, and then after the TMA pulse, because this part of the surface is saturated with TMA, it's blocked, you expose then to DEZ, the diethyl zinc. The diethyl zinc cannot bind to this part of the pore because it's already covered with transitive aluminum. That means it's forced to deposit later on in the back parts of the pore. Now, if you do this sequence, you can do various exposure times, first with TMA, and then look in the cross-section with EDX scanning. You can look into the location of the diethyl zinc. And the location of the diethyl zinc is here, which means that the initial exposure time of to aluminum oxide or to TMA of 6 seconds led to a coverage up to here. And you can measure the depth of the aluminum deposition before the zinc deposition. And in this way, you can derive the time, the traveling time of the precursor into the pore. You can derive then the diffusion coefficients which you want to have. So it's a little bit of a complicated methodology, but it's quite interesting to go with that. Now, if you look into the strike position then versus the exposure time of TMA, you have this kind of curve, and we will come to this curve just in a second again. It is important whether this curve is linear or not, because this defines you whether the reaction is diffusion limited or whether it's chemistry or reaction limited. So another point how to measure it is, this was done by Gordon. It's quite old work. We showed this at the workshop in the early conference. You can coat capillaries and then take a look in the optical microscope. You have those interference bands which frequently occur. It's very easy then with the optical microscope. You don't need to go to TEM or SEM or whatever. You just look into visual phenomena with just the optical microscope to see how deep you could get into the pore. It's a bit unpractical, I would say, because you need to have very long capillaries. But okay, it's a methodology. The third one is the quantification of the loss of hydroxyl groups. That means you use spectroscopy, you don't use microscopy here. You look into OH functionalities by infrared spectroscopy, for example, and you quantify this but just by looking into the peak of OH and how it loses over time. And the loss over time is basically a consumption with the precursors. So in this case, there's a comparison of TMA exposure here, so consumption with trimethyl aluminum, and this is a consumption of OH groups with silicon tetrachloride. And you see that there is a big difference here. So here you can say that this is diffusion limited, and this is reaction limited. Means here the reaction is much slower than the diffusion, so you don't really need to care about the exposure time because you need to enhance the time anyway for the reaction. It's slower. But if you have this kind of reactivity here, it means this is a fast reaction, and your process that you have, the coating of any pore or structure, is purely limited by the diffusion of the molecules. So here it's physics and here it's chemistry. But you have also, let's say, a bit more modern way to look into those diffusions into pores, into structures. And this is something which Christoph showed yesterday shortly. There are methodologies now to produce chips. VTT does them, those pillar hole chips, where they etch a silicon structure and they etch it laterally. So you have basically a groove, and you have a channel here below this groove where you can do ALD deposition, and the ALD coating, the precursors will go into this part here, and then they will diffuse. If you allow it enough time, they will diffuse along this channel here. And once they deposit inside of this channel, they will be either consumed or they will be limited by your process parameters. In either way, you will have gradient here for your deposition. And once you remove this roof after the process, you can just see with your bare eye the color change along this line. They can produce those kind of chips with various sizes, and they did those experiments. Here, for example, these slides I got from Rika Purman. They did those experiments with aluminum oxide, for example, with a 500 nanometer gap. So if you remove the roof, you can see below the roof there was a deposition, a very nice deposition up to this point. And here you have a gradient. That means here you had exposure time which was good enough to get that far, but you could not get further. If you want to coat it further, you need to give it more time to diffuse in. Similar thing was done also with titanium oxide. These are just the graphs here. They have different aspect ratios for different gap sizes. You can analyze those results and so on. So this is all, I mean, the data itself here is not important for us. It's important to know that you have several methodologies to know how deep can you coat, how deep are you coating. And once you know that, you can look into your process parameters in order to improve them if it's not what you want to have yet. And keep in mind that the aspect ratio is an extremely important issue here for the diffusion in the gas phase of the molecules. And you need really to care about this, not just by approximately setting to a double value. This will not really help. Consider your structures and go further into the diffusion of the molecules. Consider also your chemistry if you have plasmas, so that's important. Now, what else to consider there? Of course, the diffusion is one thing, and you need a long time to get your high aspect ratio structures coated. But if you operate at higher temperatures, you have also the critical point that some of the precursors will start decomposing. They may not start decomposing at exactly this point here. They may also start decomposing a bit earlier. That means if you want to coat high aspect ratio structures with TMA at 330 degrees C, you need to extend the time. And this extended time will lead to enhanced thermal decomposition over time of the precursors, so you will have a parasitic CVD here as well. So it is not only the time, it is also the temperature versus time and the stability of the precursor. So you see, ALD is getting more and more complicated. The more you think about it, the more you think about the physics and the chemistry, it's getting more and more complicated. So thermal decomposition plays a role as well, especially also with DEZ. People think diethyl zinc is such a thankful material. It's actually not. It decomposes quite early, so this is the literature value. It starts decomposing also earlier already. There is a reason, if you think about the literature, what it says about the ALD coatings or the growth cycles with aluminum oxide and zinc oxide and diethyl zinc and so on. Diethyl zinc is around 2.1 angstroms per cycle, while all the others are somewhere around 1, 1.2, 0.7, 0.8. And well, it has to do with a little bit of parasitic CVD as well with the dactyl zinc. We did some EFT calculations some time ago that DZ already at 100 degrees has a certain self-decomposition which results in some zinc radicals or ethyl zinc radicals flying around. So keep this in mind, that zinc is not really that stable as it's supposed to be. Just a side information. Okay, you have also to consider in those four structures reversible absorption. So you have some films, and I think yesterday, again, I think it was Nico talking about the ruthenium. It's a very similar case. You have films which absorb part of the precursor, and they release them during the next cycle. So you have a parasitic CVD happening while releasing the absorbed precursor. Not adsorbed, but absorbed precursor. It happens here, it happens also with the ruthenium. You have the oxygen is then released during the next cycle, which leads a little bit to a modified chemistry there, and it's not a pure ALD process in some cases. In those cases where you have, for example, water absorbed, this water may evaporate during the next cycle. Unintentionally, you bring together the two precursors which are supposed to be separated just because during the next pulse you have from the bottom the next precursor coming, and therefore you have a parasitic growth. You need to also consider this because in this case also you will have a non-ideal situation for the growth, in, for example, pores. No matter whether you have your diffusion times adjusted properly, you will still have these issues. So, if you want to have a high step coverage, not sure whether this will be the case in many of the projects here, but I think you will do some testing of the ELD or MLD in many situations, also in high temperature structures. You should really keep in mind some general rules for high step coverage. You need higher doses of precursors, of course. You have a very high surface area. Don't underestimate it. Small pieces of samples, they really can have a huge surface area. People really tend to underestimate that. You will need longer exposure times, and those exposure times are very much dependent on your aspect ratio. You need to have precursors that have a high volatility. Well, this is valid for all ALD precursors. They should not decompose. They should ideally not need plasma actination because of what I mentioned before. You have a higher recombination rate. That means the lifetime of those plasma-based precursors, reactive precursors, is very short compared to others. They should not be absorbed by the film of the substrate. What I just said before, water should not be soaked into the substrate or oxygen. They should not etch surface. I did not talk about that. There are some precursors which etch away the surface. We heard this yesterday also in some talks that, for example, what was it? TMA can etch zinc oxide surfaces. So just by converting the zinc oxide into dimethyl zinc, which evaporates again, so you etch the surfaces. And here you have also the problem that during the deposition, if you have some substrate or previous deposition, you may etch it, so you should not. You should look into that. And you should not have absorbing byproducts. And this is a very, very, very important issue because it's sometimes misleading if you, and I'm sorry to go back. Where is it? Here. If you see such a structure, here, for example, with titanium oxide, you say, my dose of the precursor was, or the exposure time was too short. That would be the natural conclusion out of this image. So, again, what we did here is, we had porous alumina, we coated with titanium oxide, this is the structure from the top. Then we etched selectively away the aluminum oxide, partly. So this is the remaining aluminum oxide here, and the titanium oxide is here. You would naturally say, okay, this is too short exposure time. In this case, it may not necessarily be the only case. With many processes, you have byproducts. Byproducts during the ALD process which contaminate the surface behind. That means if the precursor comes in here and it absorbs the next second precursor, for example water, you produce isopropanol or you produce HCl. And those molecules, they can penetrate deeper, they are small, they can penetrate deeper and deposit beyond the coating. And they will contaminate the surface. That means the next titanium precursor will not be easily able to bind. And this happens very, very often, also with, especially with titanium, we have this in many cases with isopropyl oxides and chlorides, depending, of course, on the substrate. So this is what I meant here with come on, absorbing byproducts. So you also have to care about that, and maybe in some cases you need to adjust the temperatures even more to desorb those byproducts. Or in some cases it doesn't help and you need to change the precursor which you use. So keep all of these things in mind if you want to go to higher tolerance. Oh, I thought that would be further. Okay, so we had the step coverage, the pores, we had the surface diffusion. These two things happen during an ALD process, and there is a third one which can happen during the ALD process. Again, substrate related. First we had inert substrates, then we had porous substrates. The third one is, and this is going to affect many of you, is if you have polymeric substrates. If you have a polymeric substrate and you want to do an ALD coating, what can easily happen, like in this example, so this is a biopolymer, but it really doesn't matter too much. You may have a coating on top of your polymer, so it's a cross-section of a silk. This is a coating around, but the problem is that below this surface you have also a deposition. It's inside of the polymer. So it's not on top, it's also inside. So both of them are happening at the same time. And this means that you also have, besides the diffusion on the surface and so on, you have also the possibility of an indiffusion of the polymers into the substrate, if the substrate allows it. So, what is happening there? I don't want to derive the whole story here in terms of mechanism or the diffusion theory behind it. You can really read it very easily here in this work from the review from Lang and Sigo and Materials Horizons. It's from last year. It's a very, very nice paper. It deals with the physical chemistry and the diffusion mechanism behind this indiffusion of precursors during an ALD process, or actually in this case, it's not an ALD process, it's an infiltration process into polymers. So we were considering for pores several possibilities here. You have the Knudsen diffusion. There are some people, depending on the pore size, they think about the viscous flow, so this is also a possibility to make a model system. If the pores are very, very small, you have molecular sealing. But if you don't have pores as such, if you just have a substrate which is less dense, it means the porosity is on the atomic level, you don't have a diffusion mechanism of that kind. You have a solution in diffusion, so you need to consider your substrate not being a physically porous structure. You have to consider your substrate being a liquid, a very viscous liquid, where materials dissolve. And the materials which dissolve are basically your ALD precursors. So they are coming to the solvent, the substrate is the solvent, they are dissolving there, and they need to diffuse through the polymer if they are able to do it. So the point is that you cannot, in this situation, consider Knudsen diffusion, of course, as a main issue. Knudsen diffusion could be considered only if your polymer substrate has pores. That means if it's a sponge. But if it's a bulk polymer, you need to really think about this solution diffusion mechanism. And there you need to consider several physical chemical parameters, for example, the solubility of the precursor inside of the polymer. You need to consider the chemical nature, process temperature and so on. So many factors which you know from physical chemistry. Most of you are chemists or you have studied physical chemistry as well. And you pass through all of those issues in terms of calculations and model setting up. At the end, basically, you start thinking about this situation. You have a precursor, it comes to the surface of the polymer, it's absorbed, it diffuses, and if the polymer allows this situation in terms of chemistry, then the precursor will bind to these functional sites of the polymer, and you will have a material inside, trapped inside of the polymer, that means in the subsurface area. Now you have to consider several points here in terms of building up a theory around it. You have Henry's law, which you can put in here. You have von Hoff's relation, which you can insert here. But the Henry's law you can put into the Fick's equation and so on. So I will not go into detail here. This is not really that important. You can really look it up in Mark's paper. The point is you need to just consider the flux of the materials after being dissolved in a Polyberg solvent and then diffusing through it, if you want to think about it. Now, the polymer is, however, not a static system. It means each polymer has a glass transition point, and with the glass transition point you have also change in the polymer volume, which you need to consider. Again, in that model, you need to think a bit further. From the first Fick's law here, you have only a static consideration, but you need to think about the dynamics, you need to think about your polymer and which temperature you are operating. Are you going to treat your polymer below Tg or above Tg? And what is the relation of your volume to the diffusion in those different regimes? At the end, after all of those considerations, you will end up with considering the second Fick's law here for some of the, well, you can do it for linear geometry here or for fibers. But then you need also to add a reactivity parameter. I think this is going too far for most of us. You will never consider this. This is just for you to give an idea that this is a different situation than having a diffusion into pores. You have really a solution of a precursor molecule in a polymer. And this will require much longer time than a diffusion of a precursor into a pore. But if you do it, you can really have a subsurface growth there. That means the polymer will absorb precursors and you will have a growth inside of the polymer. That means your precursor molecules, if you treat the polymer, will, in most of the cases, grow not only on top but also inside. And this is some work from North Carolina. I think Jesse knows that work very well. Probably. There is a temperature dependence, of course, also for the diffusion. So this is cross-section areas. I think it was, I did not copy it into here. It's PA6, but I think it was trimethyl aluminum, so aluminum oxide grown inside of polymer fibers, so polyamide fibers, so nylon 6 in this case, independence of the temperature. So you see that there are different shapes of the infiltrate and different gradients. The different depths which you can have here. And those, of course, will also change the properties of the polymer. I did not say at the beginning of this part that this is something which happens really very, very often in polymers, and you may or may not want to have this. Basically, the whole infiltration story started with an undesired observation from Steve Jobs' group that if you want to coat polymers by ALE, you have something diffusing in. So we picked up on that and looked a little bit further into that because we wanted to have it then afterwards. We wanted to have the infiltration, so we modified our processes in order to get the infiltration. But you may, in your work, want to have it or not if you do treatment of polymers by ALE. So please be aware that the precursors, in many cases, will be able to diffuse into your polymeric substrates. And if you don't want to have this, you need to react appropriately. That means you need to set up your process parameters in a way that you avoid as good as possible this infiltration. Unless you, of course, want it. If you want it, you can have many benefits out of here. For example, if you have diblock copolymers, which you then infiltrate. This is some of our very old works where we did diblock copolymeric structures inside of porous alumina. So it's two polymers, helical structures. And then if you do zinc oxide infiltration, you can basically deposit a coating on the interface between those two polymers. Then if you remove the whole template, you will end up with some structures, which are helical in this case, zinc oxide. So it's a very nice way to do some structuring. You can also infiltrate Teflon. So be aware, even inert chemical substrates like Teflon, where you consider this is not going to react at all. Zinc oxide is able to modify to make Teflon brittle, even at 70 degrees C. It's going to infiltrate, it's going to modify the chains of the polymer. What's happening there, we did some spectroscopy and some modeling here, DFT modeling. These zinc oxide units, the diethyl zinc, actually the diethyl zinc or the ethyl zinc radicals, this is what I mentioned before with the DFT modeling, they are so reactive that they can even react with the inert Teflon and then crosslink, and if you crosslink you lose all the properties of Teflon, so it's good. So even this kind of material can be infiltrated, so maybe of importance for you to keep this a little bit in mind. So for characterization, if you want to see whether and how deep you infiltrate, again, cross-sectional electron microscopy is a straightforward way to do it. It's not so easy, but it's the best way. You make a FIV cross-section of your polymeric structure, and then you take a look either with a contrast, a mass contrast, or EDX, and you will see how deep you get in. You can do thermogravimetry to identify how much of your metal is inside of your final hybrid. It's actually a hybrid material. That's what I didn't mention here. Your polymer, which you infiltrate with inorganic material, if it binds, is going to be a hybrid material. So if you then have your hybrid material, you do TG, and with TG you can have the mass percentage. You can use in situ quartz crystal micro balance to observe the mass uptake during the process. It's a possibility. Of course, you can look into FTIR for the altered chemistry. You can see chemical groups of your polymer backbone being consumed or altered with your inorganics. But you can also, of course, go further with ellipsometry, XRF, and so on. Many of those methodologies we have in the whole consortium here. And I think it's a great opportunity. That's why I put those slides here on the ways how you can identify the materials. It's a good opportunity to for you to really look into the other group's capabilities. This is a network. So this is a network, and all of you are going to work together towards a goal that each of you will finish at the end with a PhD. But if you need to do some investigation of that kind, it's the easiest to do this within the network if it's available. So don't be shy to contact your colleagues around if you need to do, I don't know, XRF, or XRF can be done here, for example, or anything else. I think it's really a great chance, because there is rarely the opportunity to have so many possibilities in one box as we have here. Okay, so this was infiltration. If you want to restrict your process to coating only, so you don't want to have an infiltration, you just want to coat, of course, you need first of all to apply as short as possible exposure times. That means you want to restrict the binding only to the surface. You don't want to allow the particles to go into the polymer. That's one thing. Then, if you use as low as possible temperatures, you are way below the glass transition point, glass transition temperature, which helps to prevent also precursor to penetrate into the polymer as good as possible. If you use larger precursors, they will absorb into the polymer and dissolve more slowly, which means also bulky precursors are going to help you to restrict to coating only. You can also allow a parasitic CVD in the initial stage, just to block the polymer surface. And in this case, the next ALD processing steps will only see an inorganic surface. That means you coat and you prevent, You prevent the precursors to see the polymer in this case, just with a little bit of CVD at the very, very beginning. You can try to cross-link the polymer on the surface chemically with organics to just lower the capability of uptaking precursor molecules. And you can, of course, also lower the precursor dose, because then you have effects on the osmotic pressure outside and inside of the polymer. Several ways. You can develop more if you want. I didn't have any further in mind at this point, so therefore there is some space here. Okay, so this was what I wanted to say for diffusion processes during coating. So substrates are important. The physics of the substrate is very important. Surface diffusion, diffusion into pores, and so dissolution into polymers, diffusion inside of polymers. Now, if you avoid all of this, and you have your coated structure, you will be happy that you have a coating on top. But then you start sometimes treating your sample, heating up and so on. And here again, diffusion processes can occur. So even if you avoid those during the process, you may encounter some of them which are going to come now. This will be a bit shorter than before. I just wanted to mention a few processes which we observed in the literature and in our own labs. You need to be aware of them in case that you need to heat treat your sample after the process. The first case, so this is case 4 in the sequence here, is that if you have two solids, so we're not talking about polymers anymore, if you have two solids, at the interface of two solids, you will have also diffusion processes, if you heat high enough. And this interfacial diffusion, well, can be induced thermally or with E-beams or whatever, and it can be equilibrated or not. What do I mean by that? In some cases, this is just an example, you will have a solid like magnesium oxide, for example, so many materials work like that, just one example. And if you coat by aluminum oxide and you heat treat this one, you will have a migration of the magnesium oxide towards the outside and aluminum oxide towards the inside. It's a solid state interfacial diffusion reaction, and at the end you will end up with a spinel magnesium aluminum oxide, which will be a very, very nice structure. Looks like that, tubes and whatever. But you had a diffusion. That means you produced out of magnesium oxide and aluminum oxide a magnesium aluminum oxide spinel. Those structures here, okay, I should have probably taken a different example because it's a little bit misleading. Those structures look hollow, but they look hollow because the core was then dissolved in non-consuming magnesium oxide. But okay, still, this is an equilibrated diffusion reaction. That means the speed or the diffusion speed of the two sides was equal. And it was equal because you had ions, magnesium and aluminum ions, which counter-diffused, but they counter-diffused into the same lattices. That means you had a stationary system of oxygen which preserved the speed of the movement or the diffusion of the material, of the ions. At the end, you had an exchange 1-to-1, basically, or charge balanced 1-to-1. But this works in many systems as such. That means you will have many situations where you have two materials. If the materials show a similar lattice in the crystalline state, it will just exchange and you will make some ternary or even quaternary structure. And you will have here the diffusion of ions. In some cases, this diffusion is not equilibrated. And if you see this, it's a structure, it's a solder ball. You know, in electronics, you are soldering with tin and some mixtures of copper and whatever, silver. And this solder becomes porous after a while. This was something which was observed by Kuykendall, a guy several decades ago. And he was wondering what happens back here that produces those voids at interfaces of materials. And what happens here is also diffusion. It's a very, very similar situation like here. Just this diffusion is not equilibrated. So if you do an ALD coating, for example, you have zinc oxide and you coat with aluminum oxide and you heat it up, what will happen is that you have voids. And this is the Kuykendall effect, what is happening here. It means you have a diffusion of materials which is not equilibrated. In an equilibrated case, no voids. In an unequilibrated case, you have voids. And those voids happen because, this is another example. So this is one of our works where we did a zinc oxide nanowire and coating with aluminum oxide. And then we have this non-equilibrated diffusion, zinc oxide diffused to the aluminum oxide, producing a spinel, and left a void, a pore behind. So we had a nanotube. But what is happening here? The point is you have a much faster diffusion from one material into the other than the opposite. And if you have this non-equilibrium, you can consider this being as movement of voids. So you are left behind with some voids. They are created because of this material diffusing quicker than this one. And those voids are going to merge at some point, and they will even enhance this effect then because they are going to act as sinks, energy sinks for the diffusion. Again, this is going much into physics, into diffusion physics. But the key point is, if you have such a material diffusion, ion diffusion, which is non-equilibrated, you will end up in having voids in the structure. And this is just because of your thermal treatment at the which then generates those voids at the interface between two materials. In this case, you don't have the same lattice, or not even a similar lattice, and therefore the rearrangement of the crystalline structure is triggering this void generation. Because you don't have, for example, oxygen here as a stationary system, which is the case in this case. So you have the oxygen being stationary. If the lattices are different, the oxygen is not stationary, so it's going to migrate as well, and then it's going to generate the voids. So interfacial diffusion is an issue in many of the materials, and you need to be aware of them as well. Okay, then you have gas diffusion possibilities, so this is on page 5, through coatings. And I think this is something which is very important for some of you who are going to deal with, for example, barriers. You can produce ALD coatings, and they will be very nice and stable over time and so on, but depending on their thickness, and the material, of course, and of course the crystalline structure, so all of these effects play a role. They are going to allow or not gases to permeate. Barriers are nowadays very important for electronics, organic electronics. We discussed about that here in the group. So you want to create coatings which are effective in blocking gas molecules from diffusion. If they are too thin, or if they are crystalline, if they have too many grain boundaries, they will allow gas permeation. And what this looks like, here an example from a scientific perspective. This is a copper oxide nanowire coated with aluminum oxide. This is just a very thin film of, I think it goes 5 nanometers or something like that. And then, if you expose it to hydrogen gas at elevated temperatures, the gas can permeate through the coating, and it can reduce this copper oxide to copper. And of course, copper oxide has a larger volume than copper. That means you have a shrinkage of the material inside here. So this coating, even without being cracked or detected, will allow gases to pass through. Of course, it's dependent on the type of gases. A small molecule like hydrogen will more easily goes through than water or whatever. But still, you have the permeation possibility. That means here you reduce the volume, which is an indication that you really reduce the copper oxide to copper. That means this really works without even cracking the film. The film itself is permeable for many of the gases. Another case is if you grow coatings which are not purely inorganic. Now we are coming to the high coat here. You have NOD or hybrid materials that you grow. This material is also pretty much permeable. So this is an example where a coating was done with dense aluminum oxide, and this is a coating done with alucone in this case, so hybrid organic, aluminum organic coating. And what you may or may not see here, I'm not sure whether you can clearly see it, this looks pretty smooth in terms of gray, and this has those whitish spots. And this coating is less dense, and it's pretty much permeable, not only for gases coming in, but if you heat up such a structure, what can easily happen is that the material coming inside can migrate to the outside. It means those materials, those coatings are already that permeable that even material transport can happen. In this case, it was copper to diffuse through these porous coatings to the outside and to precipitate as material to the outside. It was very, very obvious that this happens. And you can even see it, for example, on EDX scans. Here, this is the copper inside of this shell, so it's not copper migrating around, it's going through the coatings. So the more porous and the less dense your coatings become, the more possibilities of permeation, diffusion of either gas molecules or even materials you have. You should be aware of that when you generate your coatings, because it may not be what you actually want to have. So there is a contradiction in the way of thinking of having gas permeation barriers based on hybrid coatings, just from this point of view. And the idea here in this network is, for example, as one of the tasks, to achieve these kind of barriers, which based on hybrid materials, well, applying some tricks or whatever, making multi-layer coatings. We need to see how to do that. But whatever we do will be something new, because nobody did it before. Of course, we want to make some new progress in this process. So, hybrid coatings are cool, they are nice, they are flexible, but they are permeable. And think about these diffusion possibilities through your hybrid coatings. Okay, coming to an end. A lot of diffusion happened here. I think, or I hope that you understood that diffusion plays an important role. Diffusion in many, many aspects. You have the possibilities of diffusion on top of a surface, into a substrate, through a coating, in both directions, into pores. So there is many, many, many diffusion phenomena which can happen during the coating or after the coating. And you need to be aware of them, because it's not a static system. ALD is something dynamic. Either you have problems during the process or you have them afterwards, and if something doesn't work, you need to go to the beginning to change the parameters. If you have some of those things in mind before you start your process or setting up your process, you may avoid spending a lot of time later on with iterations. If you just think about, oh, I need longer exposure times, and they should not be only linearly increasing, they should be increasing to the square. It's already an important point to know. So, high speed ratio structures, they really need long time. Polymers, I think this is also very important. Polymers are able to absorb much of your precursor. They will just dissolve it, they will solve it. And if you don't want to have it, you need to have the appropriate measures. If you don't take those measures and you did not expect infiltration to your polymer, don't be astonished that your polymer changes all its properties. So all the infiltration work which was done so far led to mechanically altered polymers. That means what I showed here quickly was the Teflon. Teflon became brittle, although it was flexible before. Some of the things became mechanically more tough, stable, whatever. Some things became worse. So your polymer which you are possibly handling while coating may change its properties, its physical or practical properties in an undesired way. It may also change the coloration, for example. So this can all happen if you infiltrate polymers. So if you don't want to have this, then you need to take, again, those measures to prevent this infiltration. The treatment of coated substrates is also a very, very important point here. Don't forget that with the ALD coating, the story is not ended. Your coating may change also afterwards. It's not a static system which is there. Some of the coatings even just decompose in the air. So you need also to be aware of that. So they decompose, they change. But if you do a post-treatment of your coated substrates, you may easily change your coating itself. It may be different crystallinity, different material which you generate, different porosity, different density. All of this. Again, diffusion phenomena play a big role. Okay, so that was it from my side. I want to thank you for listening to me today morning. This one in almost a half hour. This is our team in San Sebastian, so this is one of the partners in the consortium here. Two of the girls are sitting right here, and while the rest of the guys is also very helpful in case of need. So if you need support in anything or what we can do for you, let us know. Thanks a lot.
Very much. Any questions?
Of course, you should also diffuse within the consortium.
Maybe one question myself. For the infiltration, you mentioned yourself that and going into really pores and like anodize the lumina and so on takes already a relatively long time in regular ALD. The infiltration into polymers is probably, into the bulk of polymers is probably even slower. So you had one slide on methods trying to avoid it.
Yeah.
If you want to use it as a methodology to really make new materials, you would also like to enhance it. So I guess on that slide you could like inverse all of the things that you mentioned. But are there like certain recommendations that you have in trying to speed it up? Or
Yes. This is also what we are working on and what we are going to work on also in the framework of this project. If you do the infiltration, and if you want to intentionally work with infiltration, it's important to make a selection of the substrate functionality and the density what you have. Yeah, the temperature is very, very important. It means if you are above, this is the sketch which I showed there also with a glass transition point. If you're above the TG, you have more free volume, so you have all of those precursor molecules stretching, the polymer molecules stretching, the chain stretching, and then generate a bit more volume because it's expanding. But you also need to adapt the pressures of the polymers, of your precursor molecules around. So you need to work with the polymer substrate, you need to work with the pressures and the temperatures and all of that. And we are looking into all of those possibilities, how to improve it. Of course, it's not that straightforward. It always depends on each individual system. It means each substrate, polymer, and precursor combination will give you a different situation, and you need always to adapt to all of that. Recommendation is, if you want to intentionally do it, take a long time for it.
Other questions?
So you talked about if you want to do formal coatings, try to avoid plasma, because with plasma you have the fast recombination, and with thermal processes you don't. But where do you put ozone on the scale? Because it's halfway in between energy enhanced and thermal ALD, but there's also a certain recombination depending on temperature, depending on...
Yes. Well, you know, the slide should not be taken too seriously in all the details. You know, the ozone deactivation is also a function of the pore depth. That means with ozone you will get deeper than with oxygen plasma. But you may not get, I don't know, to aspect ratios of 1 to 10,000. So it was there just to kind of give you an idea. Also this may be a critical point. But sure, if you work with normal materials, porous materials, you're perfectly right, ozone should be perfectly enough. And we did it also with ozone for some of the cases, so up to 1,000 aspect ratio, it's perfectly fine. Just if you really go to extreme aspect ratios, then you might have a problem with ozone. Plasma won't work anymore.
Thank you very much.